Hola, chaps. Let's learn. Hola, chaps. Mr. Turek here. This is for chemistry. Some more work with the calculator and the heating curve. So I have the same heating curve I've drawn many episodes now that shows temperature increasing up the y-axis, energy increasing as you go to the right, and for any given substance, it starts off in the solid state, then it has a horizontal curve where it is melting if it's going to the right, freezing if it's going to the left. Then it's in a liquid state. As you add energy, the temperature increases, but only to its boiling point, or yeah, and then it boils to the right or condenses to the left and turns into a gas, and then you can increase the heat from there. Great. Well, in previous episodes, we've dealt with one substance in either solid, liquid, or gaseous state, did some heat energy calculations. Then, later episode, just melting it or vaporizing it, boiling it. And then, next episode or so, the same one substance, but with two parts to actually undergoing a phase change. So I'd heat it up and then melt it and turn it into a liquid and heat it some more. One substance with two parts to it, so a hot part and a cold part. And how do you calculate the final temperature when they meet somewhere between? And now, my favorite one of all, two different substances. I guess I should mention the previous episode was, I think I just said that. So one substance, but in two different states at the same time initially, like ice in water, and they melt. So now, the one that I really want you to become masters of. I mean, all that was just preliminary warm up for this stuff. So now the end state of this is, can you deal with two different substances starting at two different temperatures? If you think back to a demonstration video I did in my backyard, I took three hot cubes out of a pot of boiling water, and one at a time I put them into a calorimeter that had room temperature water in it, and we watched the thermal probe reach some sort of equilibrium temperature as 5 minutes of time went by. So that is what you should be able to do mathematically. Take any two different substances and combine them. Fortunately, you've studied every one of my videos very carefully and practiced on your own and are now ready for this challenge, right? So the first challenge, first example, I have a container, and the container has 125 grams of ethanol in it, and it's at 0 degrees for ethanol. And into it, I put 125 grams of hot lead that is at 320 degrees Celsius. Calculate, please, what is the final temperature when this mixture of hot and cold substances finally get to equilibrium. So you're going to have to use the reference sheet quite a bit. And as we look at this, I would worry that it's going to be complicated. And my strategy is, well, there's a lot more ethanol than there is lead, but ethanol has a very low boiling point, 78 degrees. This starts off way above it, so there's a probable or possible phase change that's going to take place here. I suppose my first step would be to see how much heat it takes to raise the ethanol from where it is to the next horizontal level. So it's at 0 degrees, and for ethanol, its melting point is negative 114 degrees. So this is liquid methanol, or at least it's not solid. It's above the melting point for the solid. It's below its boiling point of 78 degrees, so it's in a liquid state right now. And I think I would start off by calculating how much heat would it take to raise that ethanol to its boiling point, and then pull that out of the lead and see where that puts me. All right. So my first step would be to heat the ethanol to its boiling point. Q equals mc delta T. The mass of the ethanol is 525 grams. The specific heat of liquid ethanol is 2.4 E042 joules per gram per degree Celsius. And the change in temperature is from its starting point, 0 degrees, to its boiling point, 78 degrees. So in parentheses, 78 minus 0. So I'm just going to put 78 degrees C and calculate, well, how much energy would that be? And I get 98.3 kilojoules. 98.3 kilojoules. Okay, well, I'm going to take that amount of energy away from this hot lead and see where that puts the lead. So I'm assuming that the ethanol is going to take at least that much heat energy away from the lead, cooling down the lead. So for lead, it's Q equals mc delta T, and now it's going to be the mass of the lead, which is 125 grams, and it's well below its melting point, unlike the surface of planet Venus. And, well, not well below. The melting point of lead is 327 degrees Celsius, and I'm at 320 degrees Celsius. So I'm close to, but still below the boiling point. So I'm dealing, or melting point. So I'm dealing with lead in the solid state. And therefore, I use the specific heat for solid lead, which is 0.130. So 0.130 joules per gram per degree Celsius. And what I really want to do is turn this around and calculate, well, how much will the temperature drop if I remove 98.3 kilojoules of heat from that lead? So I'm going to solve for delta T right now, realizing that this is a minus sign, that I'm losing the temperature. It's going to be a negative delta T in the end. And I power up my calculator, and I use the previous value that's still on the display, which you can't see anyway. What if I darken this just a little bit? Then you could almost make it out. No. I can see it here easily. You can't see it there easily at all. So I had 28.3 kilojoules. And now what I'm going to do is divide that by 125, divide that by 0.130, enter. And it says the change in temperature would be 6,050 degrees. Wow, 6,050 degrees. So clearly, I've been wrong in my assumption. There's no way the temperature is going to drop below absolute zero. And this change in temperature for that much heat energy means that's not the story that's playing out here today. So let me rethink how I would solve for the final temperature given my first assumption proved to be false. It's false because I can't drop the temperature of lead below the coldest substance that was in the container, which was at 0 degrees. I can't go 320 degrees minus 6,000 degrees. Oh, that's going to be warmer than 0 degrees. No, it's not. So clearly, I was mistaken about the lead. It's only going to cool down until it meets the temperature of the warming up ethanol. And so now I'm going to say, well, there's no way the ethanol is going to be heated up even to its boiling point. And so therefore, I can just treat this almost like the previous video where I had ice and water, and actually not even that. At the end of that, I had liquid cold water at 0 degrees and warmer water, and we solved mathematically for that one unknown, the final temperature. So I can do that here. This time around, I'm going to say Q equals mc delta T, and the heat lost by the hot stuff cooling down, which is lead, is set equal to the heat gained by the cold stuff warming up, which is ethanol. So for the cold stuff warming up, I'm going to write that as a positive expression as 525 grams times 2.440 joules per gram per degree Celsius times, and I'm happy I picked 0 degrees as the initial temperature because that means in parentheses, this would be T sub final minus 0, and then by distributive property, it goes away. So really, it's going to be just T sub F in the end. That is the heat energy gained by the cold ethanol warming up. And I'm going to set that equal to the heat energy lost by the hot lead cooling down. I'm going to flip the minus sign, so I express this as a positive quantity on the right, not a negative one, even though I'm calculating how much heat it loses, okay, gives away. And so I put in the mass of the lead, 125 grams, the specific heat of solid lead, which was 0.130 joules per gram per degree Celsius, times, and what I should do here properly is final minus initial. I'm going to flip that around and write it as initial temperature minus final temperature. So 320 degrees C minus T sub F, and I ran outside my little boundary, but you guys can squint and read that, right? 320 minus final temperature in parentheses. Great. This is an old Math 1 problem. There's only one unknown in this entire thing. So power up your calculator. 525 times 2.44, enter, says 1281 times the final temperature on the left side of the equal sign equals 125 times 0.130 times 320, which is, interestingly enough, exactly 5,200, minus 125 times 0.130, enter, 16.25 times the final temperature. Okay, I use the distributive property. I got rid of the parentheses here by going mass times specific heat times initial temperature minus mass times specific heat times final temperature for the lead. And so now it becomes more obvious to you, oh yeah, this is a Math 1 problem with just one unknown. I need to combine like terms, simplify, right? So I'm going to add 16.25 times T final to both sides. So 16.25 plus 1281, enter, is, it says 1297.25 times T final is equal to 5,200. Now I should round that off, but it's in my calculator. So I'm just going to type in 5200 divided by second answer, and it pulls up this number, the most recent calculation, and it says the final temperature is dun 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 4 point, call it 0 degrees Celsius, which you might be able to see there even, right? Trying to make this so you can see things more easily, and it's just not working out that well. Oh well. So there's the first one. Contemplate that one for a moment, right? It's logical because the final temperature is hotter than the coldest substance and cooler than the hottest substance that we started off with. Apparently, lead doesn't hold heat very well, hence its specific heat is very, very tiny, even compared to ethanol. Ethanol has what, 20 times the heat capacity of lead? Close to 20 times. So for every 20 degrees that the lead would drop, the ethanol would rise by 1 degree if they had the same quantity of both to start off with. But it turns out I have 5 times as much ethanol as I do lead. So if I thought about those two things initially, then I suppose I could have anticipated what would have happened in this case. All right, so I'm going to pause and then set up another one for you right away. All right, pause. Okay, just resuming, I wanted to make up something. So here we go. Let's do another problem. Getting it ready for you, and let's see. Honest. Okay, so suppose I have 20 grams of copper at 100 degrees C. It was just faster than me, you staring at me as I think of random numbers. And I put it into 150 grams of water. And the water is initially at 20 degrees C. These particular values are not entirely random. This was supposed to be an activity that we did. So you students were supposed to work in pairs, take a calorimeter, a thermometer, hot plate, put some water on the hot plate. Yes. Put some water on the hot plate, put these 20-gram masses that we have in our science building, which I brought home, in the water on the hot plate, get it to equilibrium at 100 degrees, and then using the tongs, put it into this amount of water inside a calorimeter and use the thermometer and, you know, measure the final temperature. As I think about it, what I really did in previous years is I didn't put the copper in water. I put the copper directly on the hot plate. And so the question became solve for the initial temperature of the copper as it sat on the hot plate that was cranked up to full. More interesting problem, right? But this one here, calculate please, what is the final temperature when I take a little 20-gram cube of copper at the boiling point of water and I add it to a calorimeter that's got 150 grams of water in it at ambient temperature 20 degrees. Okay, I can tell you right now that this tiny amount of copper in that big amount of water, the water's not going to vaporize. In fact, it should be kind of obvious to you, the water's not going to boil at all. It's just going to warm up some. So, like the previous problem, we can just say Q equals MC delta T, and we don't have to be concerned about phase changes. We're starting with solid copper, and it's going to be solid at the end. We're starting with liquid water, and it's going to be liquid water at the end. So I can just say the heat lost by the hot copper cooling down is set equal to the heat gained by the cold water warming up, and let's just do it. So 150 grams of water, and I have done this so many times now, right? I've kind of memorized the specific heat of liquid water is 4.186 joules per gram per degree Celsius. And the temperature is going to be, open parentheses, final temperature minus the initial temperature of the water, which is 20 degrees. So that goes inside the parentheses. That represents the heat gained by the cold substance warming up. Now I set that equal to the heat lost by the hot substance cooling down. And in this case, it's going to be 20 grams of copper. And I have to look up the specific heat of solid copper, and it says 0.385. So 0.385 joules per gram per degree Celsius times, open parentheses, and properly, delta T should be written as final minus initial. This would give us a negative heat because we're losing it. I'm going to reverse that so that it becomes a positive quantity on both sides of the equal sign. And therefore, I'm going to write this as 100 degrees C minus the final temperature, close parentheses. Great. Here's an old math 1 problem. There's only one unknown in this equation, final temperature. Go solve it. I'll try to catch up to you. So, using my calculator on the left, I have 150 times 4.186 is apparently, well, I'll call it 628 times T sub final. So I rounded off by 0.1 minus this times 20. So minus 1 to 12,000, I'll write it out, 558. That's how much heat is gained by the cold water warming up, and I set that equal to the heat lost by the hot water cooling down. So mass of 20 grams times specific heat of 0.385, and that works out to be 770 minus, yeah, right. So if I move the decimal point, this should be 7.70 T sub final. Since I got here by multiplying by 100, I get here by dividing that by 100, right? Okay, now combine like terms and solve for T sub final. So I'll call it 628 plus 7.6, since I did round up by 0.1 earlier. That was really 620. It was really 627.9. So as long as I'm going to do it that well, it says 635.6 times T sub final is equal to, and on the right side, I'm taking 770 and adding to that 12,558, and I get 13,328. Now I divide both sides by 635.6. So divide this by 635.6, enter, and I get a final temperature of 21.0 degrees C, which seems very logical to me. So that little tiny copper cube, it's the size of a sugar cube just about, put into a cup of water, raise the temperature of the water by barely 1 degree, while it cooled down that copper by 79 degrees. Reasonable to me. Okay, this is fun. Let's do another one. No need to pause since I wrote down 3 of these, right? So here's another one. Let's do this next one. I have 200 milliliters. I'm getting better at this. 200 milliliters of ammonia. And that's a volume, not a mass, right? And that's at negative 70 degrees Celsius. And to that, I'm going to add 300 grams of zinc that is initially at a temperature of 400 degrees C. So here's the same drawing I always do, right? There's this, there's that. Find the equilibrium temperature reached by these two things. Okay, so first little detail, because you're mathematically astute, you remember that at the beginning of the school year, you guys had to determine how to find the relationship between density, mass, and volume. And that if that relationship is density is equal to mass divided by volume. So if I tell you that I have a volume of 200 milliliters of ammonia, you should be asking yourself, what's the density of ammonia? In which case you go to the table that says, here's the density of different substances. Ammonia is listed as 0.86 grams per milliliter. So the mass is the product of the density times the volume. And these 200 milliliters of ammonia then 0.86 times point. Oh, so my calculator I goofed. So 200 times 0.86, enter, and it says 172 grams of ammonia is what I'm really working with. Okay, so I don't know if I should try to guess how this is going to go or if I should just go. So for ammonia, its melting point is negative 78 degrees Celsius. And I'm starting at negative 70 degrees Celsius, so I'm above its melting point. So it starts in a liquid state. Its boiling point is negative 33 degrees Celsius. So I'm going to worry that I've got a lot of zinc and it's very hot. So I suspect, I was wrong last time. I suspect I'm going to heat the ammonia to its boiling point. So I'm going to just assume that and go calculate away and say, well, how much heat energy does it take to heat this much ammonia to its boiling point? Q equals mc delta T. In this case, the mass is 172 grams, because that's 200 milliliters at that density. And the specific heat of liquid ammonia is listed as 4.70 joules per gram per degree Celsius. And if it goes all the way to its boiling point, which is negative 33 degrees, then in parentheses here, I would say that's my final temperature, minus 33 degrees C, minus my initial temperature, which is negative 70 degrees C. So you're subtracting the negative, which means yes, you're adding the positive, which means yes, you can think of this as being 70 minus 33, which I suppose is 37, right? 37 degrees C as a positive quantity. All right, so armed with a calculator. And since you're not seeing this, I'll just increase the contrast so I can. 172 times 4.7 times 37, enter, and I get 29.9 kilojoules. That's a lot of heat energy based on the previous problem. I don't know. Can I get that much out of this zinc? What happens when I remove this much heat energy from that much zinc at that initial temperature? Let's see. Q equals mc delta T. This time I'm going to solve for delta T. So delta T is equal to 29.9 kilojoules divided by the mass of the zinc, which is 300 grams, divided by the specific heat of solid zinc. Since its melting point is 420 degrees and I'm starting at 400 degrees, it's in a solid state. Good thing, because that's the only place I have data. Its specific heat is 0.388, which is a pretty tiny number. So maybe this will also fail like it did on the first example. And I powered up. So this number is already in my calculator. So I go divide by 300, divide by 0.388, enter. And it says the temperature is going to drop, really, because this is how much heat energy I'm taking away. It's going to drop by 257 degrees Celsius. Now, I'm starting at I'm starting at 400 degrees, and it's going to drop by 257 degrees. So I'm going to drop it. Let's go 400 minus 257. And so the temperature of the zinc is going to be 143 degrees Celsius. When the temperature of the zinc has fallen to this level, that means it has given up 29.9 kilojoules of heat energy to the ammonia. When the ammonia heats up by that amount of heat energy, it will have reached its boiling point. So the ammonia is now at a temperature of boiling ammonia, which is negative 33 degrees. So the ammonia is boiling in a liquid state at negative 33 degrees, and the zinc has cooled down to 143 degrees. So there's more that's going to take place. What I would do next is attempt to vaporize the ammonia. And just trying to get a guess for it, on this chart, it says the heat of vaporization of ammonia is 1,360 joules per gram. That seems like a lot, relatively. So my guess is the zinc will not be able to provide enough heat energy to vaporize all of the ammonia. So I'm going to assume that the zinc has to cool all the way down to the boiling point of ammonia, and try that calculation and see if my assumption works out to be correct. So I'm going to drop the zinc from 143 degrees, where it is at the moment, all the way down to the boiling point of liquid ammonia. And after I extract that much heat energy out of the zinc, I'm going to see, well, just how much ammonia do I vaporize with that amount of heat energy. Okay, so Q equals mc delta T. In this case, the mass of zinc is 300 grams. The specific heat of zinc is 0.388 joules per gram per degree C, and the change in temperature is going to be 143 minus negative 33, which means whatever that is, 176 degrees. And when I multiply it out, I get a heat of 20.5 kilojoules of heat removed from the zinc, cooling it down all the way to the boiling point of ammonia. What I could do to be prudent right now is see how much heat energy it takes to vaporize all of the ammonia. But I know I only have 172 grams of ammonia to work with. I'm now going to solve for how much ammonia I can vaporize, starting with 20.5 kilojoules. Of course, delta H of vaporization times the mass is the equation I want to use. I just wrote Q equals this. So using this value for Q, dividing it by the heat of vaporization for liquid ammonia, which is 1,360. Aha, okay. It says I can only vaporize 15 grams of ammonia. So I finally got one guess correct. So here's the solution, so to speak, to this solution. If I started with 172 grams of ammonia and I vaporize 15 grams of it, and 12 minus 5 is 7, and 6 minus 1 is 5. So I end up with 157 grams of boiling liquid ammonia, and H3 is the formula. I end up with 15 grams of gaseous ammonia, and it's not allowed to heat up until all the liquid is boiled. So all of this would be at a temperature of negative 33 degrees Celsius. And just to finish up the problem, I have 300 grams of zinc at negative 33 degrees Celsius. So there's the complete solution to this particular problem. I have partially vaporized the ammonia. I have cooled the zinc down to the boiling point of the liquid ammonia. All right, well, I came up with one more example, and I think it's time that you students do this one yourself, right? So I guess I don't need to rewrite it. I could just show it to you. Look, calculate, please. If I were to take 145 grams of silver that's at an initial temperature of 925 degrees Celsius and immerse it into 355 grams, oh, how kind of me, because I could have given it to you as a volume and had you do the density calculation. But I gave it to you as a mass. I guess I'm getting us to be a softie in my old age. 355 grams of methanol that's at an initial temperature of negative 110 degrees. Ooh. First of all, you should realize that negative 110 is colder than negative 98. So you're beginning with methanol in the solid state. Calculate, please, what is the equilibrium temperature and conditions for this problem. I will pause it and calculate it. You pause it and calculate it, and we'll see how it turns out. Ciao. All right. I paused, you calculated, I calculated. Let's finish it all. My result is, again, the problem was if I start with 145 grams of silver at an initial temperature of 925 degrees Celsius and I immerse it into 355 grams of solid methanol that's initially at negative 110 degrees Celsius, what are the final conditions that I end up with? And of course, I was looking at this and guessing that, first of all, I'm expecting, since it's only 12 degrees away from its melting point, I probably have at least enough heat energy in that silver to get the methanol to its melting point. So, based on that guess, I calculated I would need 9.29 kilojoules of heat energy to raise the temperature of solid methanol by 12 degrees. I then calculated what would be the drop in temperature for the silver if I removed 9.29 kilojoules from the silver. I calculated this would cool the silver from 925 degrees, drop it all the way down to 652 degrees. So, wow, almost 300-degree temperature drop of the silver just to increase the temperature of the methanol by 12 degrees. So, pretty stark difference between these. So based on that, my next expectation was, I sort of suspect that the silver can't melt all of that methanol. So I took the calculation and said, how much heat energy could I extract from the silver that's starting at 652 degrees Celsius if I cooled it all the way down to the boiling point of methanol? And the boiling point of methanol was negative 98 degrees Celsius. So pulling out that, so here's my note. I'm guessing that the silver cools down to the methanol's boiling point. I calculated I could extract 25.6 kilojoules of heat energy from that silver under that condition. And if I applied that, all of that, to melting solid methanol using the heat of fusion, which I hope I used, heat of fusion, ta-da, I got a result that I can only melt 258 grams of it, but I have more than that I'm starting off with. So I cannot melt all of the methanol. So in conclusion, my result is I successfully ended up with 97 grams of solid methanol that is at its melting point, but is still in the solid state. I've been able to melt 258 grams of that, so it's now liquid methanol, but it's also still at its boiling point, negative 98 degrees Celsius. And meanwhile, that silver that started off at 925 degrees, now it's cooled all the way down so that 145 grams of solid silver is at the melting point of methanol, negative 98 degrees Celsius. All right. This concludes this episode. This is exactly the sort of stuff I wish you students had mastered during this unit in chemistry. It might seem kind of complex to you. I've kind of sped up my talking this time because I figured, well, you could always replay the tape if you want to, right? So I've had fun with this, but from my point of view, this is essentially the last part of the thermodynamics unit. This is where I wanted you to get to, where you could take two different substances, mix them, and correctly calculate what is going to be the result of mixing these things. I would dearly love to give you a long set of calculations to do. Instead, I'm just going to say ciao for now.